Okay, so we're going to try to understand how simple harmonic motion links with circular motion, because we just saw some formulae for simple harmonic motion which has omega in it, and omega is angular velocity. It's called angular, why has it gone over there? It's called angular velocity, so we've clearly got an angle when it comes to circular motion, but there's no angles when it comes to simple harmonic motion. So what it is, and this is related to Galileo. Galileo saw moons around Jupiter, but he saw it edge on. So if this thing was moving around in a circle, we can see the angle would be increasing. The rate at which it moves in whatever angle, like the angle per second, we would call the angular velocity. So we can measure the angular velocity in a circle. And what if we were to flip this circle on its side and imagine we're seeing it head on? When it gets to this point, we are viewing it head on. So basically, if you imagine flipping this on its side, then drawing. Okay, let's try that again. I'm just going to pause this and get this set up properly. Right, so basically, I think we can get rid of those bits now. I was just lining them up so we can see that this arrow here is the width of that. This is what we would actually see if we saw this orbit head on. And so we'd see, at this point here, we'd see an object there. Okay, maybe I'll make this semi-transparent. When it goes down to here, we'd see the object, here, right? And then when it goes up to here, we'd see it over here. So what we want to do is come up with a formula that kind of like works it out for us. How does the position link to? So that's going to be around about there. You can see it lines it up properly. How does that position link to the position that we would see if we were looking at it head on, sort of edge on? So, okay, well, we've got, we can do the equilibrium point still, which will be from here. So let's make that a dotted line, and we will just shrink it down to here. So that's the equilibrium point. And it's currently what we would see down here would be that displacement. So we could call that x. Now, and then that's r. Okay, the maximum displacement would in fact be r, because it's going to be there to there. So let's see, how do we work out that that displacement there? It's going to be this, isn't it? Well, hopefully you can see that this is a right angle triangle. That's going to be r. So we just need to do trigonometry. And that's the angle it's moved through currently. And with a little bit of parallel lines geometry, that's also this angle. So we have a right angle triangle. What we want to work out is the side that's opposite the angle. So we can use which is sine theta is equal to opposite over hypotenuse. In this case, the opposite side is x, the displacement, and the hypotenuse is r. So x is equal to r sine theta. Now, let me just pause this a moment. Now, if we think of what omega is equal to the rate of change of the angle, then rearranging that, we can say that theta is equal to omega times t. So therefore, x equals to r sine theta, which is r sine omega t. That's what we've got over here. So that's where that came from. Essentially, the omega is what angle whenever we look at a simple harmonic motion system like this, we are imagining that it's actually moving in some imaginary circle. And if it was moving in an imaginary circle, what angle has it got to by whatever point? Once it's reached its maximum displacement, which should be over here, it's moved through 1/4 of a circle, which means if we plotted a graph of simple harmonic motion, we start off here, goes down like that, and then backlash, that's an entire time period. So over here, it's when it's up here. Again, that would be at its middle point, and so the displacement would be 0. And maximum displacement would be 1/4 of the term. So it's going to be there. This is x, this is t. And in our analogy, when we think of it being like a circle, the radius is basically the amplitude, because when it reaches the maximum displacement, that is when it's the radius of the circle. So this is r, or we could say if we're thinking about it as being a circle. So this is how it all connects. This is how simple harmonic motion and circular motion connect. We are imagining a circle, and if there was a circle, if we looked at the edge on, what angle has the thing moved through for us to see it at this particular point on the trajectory? Whenever we see an object on a spring going back and forth, we are imagining that. I mean, we're not really spending much time imagining it, but this is where the angular velocity comes from. We're imagining that really there's something going in a circle and it's flipped on its side, and we're seeing it going back and forth, but in reality it's moving in a circle. It's all just a way of thinking about things, and so we can think of, rather than calling it t, we could call the thing the angle, such that at a whole oscillation, then the angle would be 2 pi, and half the oscillation would be pi, and 1/4 of the oscillation would be pi over 2. Okay, right, let me just stop that.